Welcome and thank you for joining us today. This webinar will be a basic overview of nuclear medicine. So let's start with what is nuclear medicine. Nuclear medicine is a specialized medical modality where a small amount of radioactive material is introduced into a patient and the resulting images are from emissions. We typically call the radioactive material a radiopharmaceutical or a radiotracer, and a specialized detection system called a gamma camera or a PET camera will detect this radiation, or as I like to say, it acquires the emissions. Those emissions are used to create an image. The emissions are from localized organs or body functions, and they can be used to diagnose the presence or severity of conditions such as cancer, heart defects, or a lot of other issues. Nuclear medicine is unique in that it is able to pinpoint molecular activities and identify diseases at their earliest stages. Another use of nuclear medicine is in the realm of therapy. This therapy can be targeted to specific organs or functions, such as therapy for the thyroid or even cancerous tumors. Nuclear medicine generally utilizes gamma, beta, and alpha rays, which are forms of ionizing radiation. The most common form being the gamma ray, hence the detection device having the name gamma camera. So, what is a radiopharmaceutical? For the most part, it can be thought of as a form of medication and is used for diagnostics or therapy. The radiopharmaceutical is primarily made up of saline, so there's almost no risk of a reaction. In fact, you can't even feel it. It's not going to make you warmer. It's not going to make you glow. You aren't going to grow 3 heads. It's just mainly saline. The radiopharmaceutical is comprised of 2 general parts, a radioactive part and a pharmaceutical part. The radioactive part gives off its energy as the radiation decays or as it breaks down, the isotope breaks down. The actual volume that we're talking about for the radioactive part is in the millionths of a gram. There are many different types of radioactive isotopes, and each kind of have their own characteristics and uses, but the most common that you're going to deal with or hear about is technetium-99m, M standing for metastable, I believe. Some of the others you may hear about are iodine-123, thallium-201, FDG or PET, or for the PET scanners, and fluorine-18. The second part of the radiopharmaceutical, and the part is used for, as we call, it's a tag or a tracer or a label, and it's used to ensure the localization of that radiopharmaceutical into a desired organ or into a desired function. The dose, when it's given to the patient, is going to determine the total amount of radiation exposure to that patient. The number of studies done, in other words, I take 2 pictures, or how long the pictures take, all of that kind of stuff is not going to affect the dose at all, because the dose is actually coming from the patient. It's being emitted from the patient. The camera is simply detecting that radiation. The patient's total dose is going to be determined by half-life of that dose and body excretions through breathing, urination, sweat, and whatnot. As I previously stated, the localization of the dose is primarily due to the pharmaceutical part. So, technetium-99 MDP, which is something you may hear of, is used for a bone scan, where technetium-99 mag-3 would be used for a renal scan. You can notice that technetium-99m is your radioactive component. mag-3, MDP, they're the tag. All that changed is the tag, and it is localizing in a different area of the body. For those of you who like big unpronounceable words, I've included the technical names for the mag-3 and the MDP down there. So let's go on and describe radiation as it's used in nuclear medicine. Radiation is just a form of energy. And in this case, we're talking about gamma rays primarily, and so we're referring to electromagnetic radiation. In the graph below, you can see and we can visualize the forms of electromagnetic radiation, and we can categorize them. Radiation has 2 larger categories, The first of the larger categories is what we call non-ionizing radiation. It is the lower in frequency and lower in energy type radiation, and includes things like radio waves, light waves, stuff like that. Essentially, if you start at the bottom of the UV light spectrum and go down, we're going to consider that non-ionizing radiation. Not always, but we consider that. If you take the other part, if we start at UV light and go up, so the upper part of the frequencies and energies, which include gamma rays and X-rays, we're calling that ionizing radiation. Now, there is no hard and fast boundary for ionizing and non-ionizing. They're generals. So there are things that are down pretty low that are actually ionizing, but the general consensus is that lower the energy, the lower the frequency, the less ionizing, the higher it goes, the more ionizing, or not the more ionizing, the fact that it is ionizing. The term ionizing actually is talking about what happens to the cells. The term ionizing means that when the radiation is passing through an atom or a molecule, it has the ability to ionize that atom or molecule. And when that does, it liberates electrons from the atoms or molecules, and that is an effect to that atom or molecule. Basically, think of it as you're damaging it. That damage is cumulative, and that damage is immediate. So as a radiation hits you, it is immediate, but there is a cumulative effect to it. So if I had an exposure to radiation today, and I have a certain amount of radiation I receive, and then a year from now, I get some more exposure, those exposures are additive. It's not like the radiation today went away. It is cumulative. It builds over time. So your exposure builds as you go through time. When ionizing radiation affects an atom or a molecule, it primarily does it in three different ways. It damages it in three different ways. And when that happens, there are three kind of effects, I should say. When it happens, we have a cell that dies. The cell just plain out flat dies. It's just dead. We know stuff dies all the time. Skin cells die all the time. So that's not really the worst thing in the world. The cell can be harmed and it can repair itself. That's actually a pretty good outcome. The third is the one that everybody's concerned about. When a cell tries to repair itself, but it does so incorrectly, it can mutate. And if it mutates, that cell can become cancerous. And cancerous things we know are things we don't want to deal with. When we're talking about ionizing radiation in nuclear medicine, we bring it into three categories. We talked a little bit about gamma rays, but we also need to know that there are alpha and beta rays out there. The gamma rays we discussed are electromagnetic in nature, and that gives them certain characteristics. If you look at the graph on the bottom right, the gamma rays have a strong penetrating power. They can penetrate a lot of things, even aluminum. They can blow right through it. Another characteristic, though, is that they are electromagnetic in nature. That means they really don't have any mass. They're just a wave. And waves travel at the speed of light, or electromagnetic waves travel at the speed of light, so it's very, very fast. Since it has no mass and it's traveling very fast, it really doesn't have much of an ionizing effect. In other words, it doesn't have much of a damaging effect to the cells and the atoms. For the damaging effect, for the ionization, what I like to do is kind of make some analogies. So let's think of it as an extremely small item, like a sewing pin needle. And if it was to pass through your arm, it would pass through your arm with minimal damage. You know, it's really small. It's small, slender, it's sleek. It'll just pass right through with minimal damage. In contrast, let's look at the beta rays, or actually it's a particle, the beta particle. It is not electromagnetic in nature. It's actually created through decay when a neutron changes into a proton and an electron, and the electron leaves. When that happens, it causes the ionization, or it causes the ability for ionization. On the top table, you're going to see the table states that beta rays have a weak to moderate ionizing effect. On the bottom graph, if you compare the beta ray and the gamma ray, you're going to see that beta rays have a lot less penetrating power. They can be stopped by things such as aluminum and such, but they will pass through skin, paper, stuff like that. Due to the fact that we're talking about an electron escaping, and that electron has mass, we need to analogize the beta ray as being a larger particle or something bigger. So let's think of it as a pencil. If a pencil was to pass through your arm, it's going to create noticeable damage. The pin went through pretty seamlessly. Pencil is going to create damage. Its larger size ensures it's going to interact with more atoms, more molecules. Therefore, it's going to create more damage, more ionization, has a larger ionizing effect. And then lastly, let's consider the alpha ray, or the alpha particle. Again, not electromagnetic in nature. Again, they are created through radioactive decay and emission. The emission is a helium nucleus, which is 2 protons, 2 neutrons. We're talking about bigger stuff. Alpha rays are really slow, but they have a very large ionizing effect if you look on the top left graph. Bottom right graph, you're going to see they have very little penetrating power. They can be actually stopped by a piece of paper or dead skin cells. Very, very less or weak penetrating, but their ionizing effect is big. And due to their mass, the mass of the emission, which is the helium nucleus, the alpha ray, when it passes through a structure, you can think of it as more like a bowling ball or a cannonball. This much larger object is going to interact with many more parts of your cell, your cellular structure. Interacting with more structure does more damage, more ionization. So the different rays will affect you differently. Let's talk about the word radiate for a second here. The word radiate is part of the word radiation, right? It's the core of it. The word radiate is really just an effect. The word radiate describes the effect where something emanates or goes out from some singular point in all directions equally. And things that we can think of that radiate: light radiates, sound radiates, radio waves radiate, many, many things radiate. They simply emanate out from a point. I like to use light as a corollary when I'm talking about gamma rays. This is because there's a lot of similarities. When I think of light, I understand that light travels in a straight line. I take a flashlight, turn it on, nice straight line. Gamma rays do the same thing. We know that light can have different frequencies. Blue light, red light, green light. Each of those are a different frequency in the spectrum. Well, gamma rays, the same thing. There are frequencies associated with gamma rays. Each of them have their own characteristics. We know that light can be refracted or reflected. You know, in light, we think of mirrors and shiny surfaces. Well, with rays, or gamma rays, we think of metal structures or other things like that. They can refract or reflect. We also know that light can be attenuated or reduced. Think of fog. If you're shining a light through a fog, you do not see it nearly as intensely as if the fog was not there. Same thing with gamma rays, can be attenuated. Now this is kind of where the similarities stop. Because of the penetrating power of the gamma ray, there is no real effective way to lens them. Light, you can focus it with a lens, with a magnifying lens. I can focus light. Can't do that with gamma rays. They just blow right through things like that. If you can come up with an effective and a efficient way of lensing gamma rays, let me know, and we'll patent it together, and we'll both make a lot of money. Continuing on with our discussion of radiation, you may think, well, you know, since radiation is bad, shouldn't we make sure that we're never around radiation? Well, the truth is, the unfortunate truth is, you can't get away from radiation. The graph here on this page shows the representation of an average person's lifetime exposure, represented as a pie chart. First of all, notice 84% of an average person exposure is just from being alive. we got exposure from all kinds of sources. There's exposure from the ground, exposure from our food, exposure from cosmic rays, structures, buildings, our occupation, tons of stuff. One segment in there is medical imaging. Now that includes nuclear medicine, that includes X-ray, that includes a lot of other modalities, but that is also a component of it. But just notice, you can't get away from it. And a side note, cosmic rays are a real thing. They obviously come from the cosmos, space, and so the higher in elevation you are, the less atmospheric protection you have. The less atmospheric protection you have, the more exposure you will get. Now, this is true in airplane flights as well as living in Denver, Colorado. So if I lived in Denver, Colorado my whole life, I'm going to increase my non-medical exposure by about 30% over the normal person. This is due to the elevation, the added elevation. So I'm getting elevated cosmic rays, also because of the mountains. The mountains are built of granite and stuff like that, and those type of materials have a higher emission. If you are concerned about your exposure, there's many things you need to consider. You need to consider your location and many other things. And a lot of people, unfortunately, don't really understand that smoking also affects your exposure. So with that thought in mind, a quick question for you is, down at the bottom there, which of the following would most affect your annual exposure? Would it be 100 dental x-rays in a year? Would it be 96 coast-to-coast flights a year where I have an increased elevation? Would it be smoking a pack and a half of cigarettes every day for a year? Or would living near a nuclear plant be the most horrendous thing in the world? Well, most people are quite surprised to find out that C, smoking that pack and a half of cigarettes every day, is actually causing you much more exposure than any of the other activities listed. Before we go on, let's make a definition here. The definition is millisievert. Now, millisievert is a unit of measure, but it's describing the radiation absorbed and how the tissue responds to that. So you have to think about where the radiation is being focused and how that tissue would respond to it. In smoking, we're talking about the radiation's absorbed, or we're inhaling it. It's in our lungs. And what tissue is going to be responding to it is the ovuli of the lungs. Okay? And so that measurement is used in contrast to coast-to-coast flight. Cosmic rays are just blowing through my entire body. How's my entire body responding to it? So if I was to take 100 dental x-rays and you look at the exposure for each individual x-ray, you're going to see I'm going to get about 5 millisieverts of exposure. 96 flights would be about 4 millisieverts. If I don't actually have any information about living near a nuclear power plant, but I do have documentation that shows that if I lived 10 miles from the 3 Mile Island reactor when it had its accident in 1979, I would have only received about 0.08 millisieverts from the exposure from that accident. So really, if you look at the amount of values for the amount of millisieverts, that smoking thing is a big thing. If you are curious and you want to calculate your yearly radiation dose, I listed a couple websites here, or actually it's one website and just different links to different places in it. It's the EPA's exposure calculator. They ask you a lot of questions, tons of questions, because they want to take into account many different variables. You know, do you smoke? Do you not smoke? What is your elevation? Do you live at ground level, sea level? Do you live, up on the top of a mountain? What are, how often do you fly? What do you eat? Many, many different questions. And they will calculate what your annual dose is just from being alive. You can get a really good indication of your exposure based on your habits. If you're concerned about your exposure, you can adjust your habits and making it an effect on your exposure. The term relating to radiation that we need to understand or there's a term that we need to understand, and it's called half-life. Half-life is a term that describes the decay of a radioactive material during its radioactive lifespan. And another way to describe it is, if I take a material, how long before it loses half of its current radioactivity? If you look at the top chart, we started at time period 0, and we have 1 unit of radioactivity, which is all of it. After 1 time period, due to the half-life decay, we will have 1/2 of the original activity. After a second time period, we're going to have 1/4 of the original activity, which is 1/2 of the original 1/2. After the third time period, 1/8 of the original activity, and so on. Half-life is measured in time intervals. These time intervals can be units of seconds, minutes, days, years, decades, depending on the isotope, depending on what we're dealing with. Typically in nuclear medicine, we deal with fairly quick half-lives, and for our purposes, we basically understand and accept that after 10 half-lives, whatever we're dealing with is down to essentially background radiation. If you reference that table down in the bottom right of the slide, you're going to see the activity remaining from a 1 millicurie source after 10 half-lives is going to be about 2,000th of a millicurie, which is going to be extremely hard to distinguish from any kind of background radiation. So 10 half-lives, pretty much gone for us, for what we're dealing with. The reality is half-life has some effects on us, and there are aspects of half-life that can be seen to help us and aspects of half-life that kind of are a hindrance. Half-life is nice because it's very, very predictable. And since it's very predictable, it's very useful. It's useful for technologists and physicians when they're computing dosages to be given to patients. It's very useful for us as service personnel when we're trying to understand how long we have or how long a particular source or dose is going to be useful for us. But there are some real downsides to half-life, and this is what I want to stress. The downsides to half-life, and this is especially true if a gamma camera or the room in which a gamma camera becomes contaminated, the reality of half-life is it takes a finite amount of time for that unwanted activity to reduce to background levels. And there's no way to speed it up. I can try and clean up the radiation, but you will never get it all. You can get some of it, the liquid part you can get, but it absorbs in. You can never get it all. So it has to decay out. If an unwanted activity if you have unwanted activity and if it's elevated, it's going to inhibit you from doing service, from doing calibrations, and worse yet, you can actually stop the technologist from scanning patients. Nothing is worse than having a working camera. You need to do a PM, you come in, you accidentally contaminate the detector. This is not only going to stop your work, but it's going to prevent the site from doing scans until that unwanted activity has reached background levels. This can take days depending on the type of source. Technologists do not take kindly to you coming in with a working system and you leaving them with a broken one. One side of half-life that we also want to kind of consider is that there is a biological function in patients. This does not have to do with us as service engineers, but in the patients, there's a biological function where the isotope is excreted out, whether it's through sweat or urination or whatever. So there is a biological component to half-life. And people will take a biological component type thought process and the radioactive half-life and combine it, and they'll call it an effective half-life for the patient. So the effective half-life for a patient is not necessarily the entire half-life for the isotope itself. If you frequent a nuclear medicine department, which if you're in this webinar, I'm pretty sure you're going to, you're going to hear isotopes. You're going to hear names of isotopes, and here are some of the common ones you might interact with. The first and common isotope I want to mention is only for QA or QC, and that is cobalt-57. It exists as a sealed sheet source or occasionally as a sealed epoxy vial. If you happen to be dealing with a technologist who's been around for quite a while, you might hear the term cookie. Originally, the detectors were all round, and because the detectors were round, the sheet sources were round to accommodate them, and they kind of looked like a cookie, so that kind of was a nickname that was given to them. And so there are some technologists who still actually use that term. I still use that term occasionally. With cobalt-57, on the chart, you'll notice its half-life is 270 days. This is really nice because it allows me to be able to know that I have a sheet source or a source of radiation that I can use that will be around for a very long time, and it's fairly stable. And I won't have to replace it quickly, or they won't have to replace it quickly. The other thing to notice about cobalt-57 is its energy level. The KeV is 122 keV. The reason that is important is because of the similarity between it and the other one listed there in red, technetium-99. Its isotope KeV is quite comparable, and so it is the reaction of the system to that isotope is going to be similar to technetium. So it's a nice, convenient, consistent way of having a way of testing and evaluating the camera's performance without having to mess with a liquid and the possibility of contamination over time. The most common isotope that you will experience in a nuclear medicine department is technetium-99. It's used for many, many kinds of scans, cardiac scans, bone scans, renal scans, lung scans, etc. It has a KeV of 140 keV, and that is a number that's going to be glued into your head. It has a half-life of about 6 hours. Now, we typically say 6 hours. If you look at the graph, you're going to see, or the table, it's actually 6.02. Nobody goes by the O2 in my world. You know, when they're really, really computing things out to the nth degree, yes, they will use it. For us, 6 hours half-life. Its flexibility, and the reason it's so popular, is because of the tags that are combined with it. It is also the most common isotope for service engineers. It will be provided to you as a liquid in a sealed vial. So they'll take a vacuumed vial, they'll put technetium in it as a liquid. Now, one thing to note, you must be careful. You have to take care when you're handling that vial, because it is possible for whoever put the source in the vial to contaminate the vial. If you contaminate the vial, I grab the vial, now my hand's contaminated. Now I touch the camera's contaminated. Now we're back to nothing upsets a technologist more than having a broken camera, or a non-functional camera, I should say, because you contaminated it. So you need to be careful. The 6-hour half-life is useful, though, because when I'm done using it, I just have them put it back in the hot lab. After 10 half-lives, it's gone away. 10 half-lives is 60 hours. It's gone. It's just water after that point. And it's a really acceptable thing. Logically, what better isotope could we calibrate with than technetium? It is the exact isotope, or the most primary isotope, that the camera is going to be using. We are actually calibrating and testing with the most common thing that's going to be used in a patient. This is going to ensure that we have the most accurate representation of patient emissions during an actual scan. I'd mentioned in previous slides KeV levels. KeV is simply a unit of measurement. It is described as the energy of the emissions of the radioactive source. KeV stands for kilo electron volt. And me personally, I like to correlate KeV and its frequency with penetrating power. If I think of the isotope that is most common, technetium-99. Okay, it can penetrate aluminum, as we described before, but a moderately thin piece of lead will be enough to stop it, because lead will stop a certain energy worth of isotope or a certain keV energy. Now, if I was to take FTG or fluorine-18, which we're talking about 511 keV, it's going to take a much, much thicker piece of lead to stop 511 keV energies. In a later webinar, we're going to be discussing general gamma cameras and how they function, the concepts behind them, and we will be dealing with this issue when we talk about collimation and collimators, you know, the thickness of collimators and why different collimators have different thicknesses of septa, etc. But that will be in a later webinar. Another important concept we need to understand when we're dealing with radiation is the concept of inverse square law. It's actually, it's a law. The inverse square law describes the relationship between the intensity of an effect and distance. The inverse square law states that the intensity of an effect is at an inverse proportion to the square of the distance from the originating source. Lots of big, long, nasty words. The easy way to say this, and remember this, is if you double your distance, it's 1/4 the radiation exposure. So double the distance, 1/4 of the radiation. And that is the heart of the inverse square law. I have this graph up here describing this concept. In the graph, box A is a defined size in square inches or some kind of value. And you can see as the rays emanate, they spread out, right? The rays that pass through that A are spreading out, and as they go through further areas, you're going to see it decreases. So the last radius value, radius 3, the one on the far right, not nearly the number of rays penetrate that same size as the first A. A way to kind of put this into another point of reference is if you were to imagine a point of radiation in space, and then you place a tennis ball around it, the entire surface area of the tennis ball would be receiving all of the emissions for a given period of time. So let's say we have a million emissions, and they're all 1 million of those emissions are going to interact with the surface area of the tennis ball. Makes sense. Now, if we take that same point of radiation in space, same amount of time, but we have a beach ball around it, you're going to also say 1 million emissions interacted with the surface of the beach ball, right? But here's the difference. The surface area of the tennis ball is a lot smaller. And so the number of emissions passing through a 1 square inch of the tennis ball, there's going to be a lot more emissions in that 1 square inch of the tennis ball than there are on 1 square inch of the beach ball. This is due to the fact the beach ball's surface is further away from the source and the emissions are spreading out. Even though the entire beach ball gets them all, 1 square inch is going to get significantly less. This is the concept of the inverse square law. This occurrence or this effect does have effect on us as service engineers and on patients. When we're dealing with patients, the distance from the localized source to the detection device is going to affect many things. It's going to affect the rate of detection, because as I get further away, rays spread out, they miss the collimator, they don't get detected. It's going to affect the resolution of the structure that we're dealing with. It's going to directly affect or correlate to the amount of time or the number of counts that are acquired in a study. For field service engineers, what we're dealing with is not so much that. What we're dealing with is I have a source, I'm calibrating the camera, I want there to be less counts or more counts. I need to move my source closer or further away, depending on if it's a legitimate thing to do. Or my exposure for personal reasons. Let's say I want to decrease my personal exposure to the source that I'm dealing with. I just get further away. If I double my distance, I'm getting 1/4 of the radiation if I was closer to it. So when we're talking about radiation, the inverse square law, as service personnel, a common saying that you're going to hear is distance is our friend. You get away from it, the more distance you can generate, the better things are for you. So we've mentioned that there's 2 primary uses of nuclear medicine procedures. The most common is functional imaging, which we've discussed, but additionally there's therapeutic. In functional imaging, the radiopharmaceuticals ingested, inhaled into the body, the radiopharmaceutical gets localized into a desired part of the body or function, and that's based upon the tag or the label used. The emissions of the gamma rays, when they're localized there, are detected by a gamma camera or a PET camera. The emissions are then, the detected emissions are collected and processed, and that is analyzed and displayed, and a diagnosis is made. So the doc, the physician, the radiologist says this, that, or the other thing about your organ. Conversely, in therapeutic use, the radiopharmaceutical is sometimes injected, sometimes inhaled, and sometimes physically inserted to ensure localization into a desired part of the body or into a function. And these localizations, we use the emissions from these localizations to damage or to provide therapy to the tissues surrounding them. What we're trying to do is make sure that we damage the area that we want to damage, but areas surrounding that, outside of the thing we want therapy on, we want to make sure that that is minimally damaged. So there are some differences in the way they're used, but there are a lot of similarities also. There are a number of imaging modalities used in the medical industry today, and each of them kind of does something different or better or worse than the other guys. Nuclear medicine, we discussed, we use radiopharmaceuticals, we put them in a patient, and the patient becomes radioactive for a period of time. That radiation is localized into an organ, emissions come out of that area, is detected, collected, analyzed, displayed, and it's primarily functional information. I can look at how well a kidney or a liver is functioning. I can look at the uptake into a kidney and then the excretion out of the kidney or into a thyroid or out of a thyroid. And I can say, this is normal or this is abnormal. So I can look at the functional process in that thyroid. The thyroid might be the same size, normal size, but it might be just functioning wrong. So nuclear medicine, we think of it primarily as functional. There is some structural information. It's just not real crisp and clear. Other modalities, much more crisp, much more clear on structure. We're the function guys. X-ray CT, if we were to compare it against that. In an X-ray CT unit, basically you position a patient between an X-ray unit and a detection device. They emit bursts of radiation. In CTs, it's bursts, and that passes through the patient. It's collected by the detection device. The detection device is essentially a shadow of dense structures. The more dense a structure, the more the X-rays are attenuated. The less dense the structure, the less it's attenuated. And so we're essentially getting a shadow on that detection device that creates image, that image data displayed, again, analyzed, but we're primarily looking at structure for X-rays. If we were to look at ultrasound, the name itself implies the fact that we're dealing with sound. Ultrasound is accomplished by using a sound transducer where the sound is introduced into the body. The sound reflects off of various tissues in the body, and it's reflected back to the transducer. That transducer collects that information. It's processed, analyzed, and it generates structural information again, primarily on hard and soft tissues. Now you can do things like watch blood flow, etc., by comparing one image from another image from another image, kind of like background subtraction. So you can get some things, but you can't see my thyroid is not uptaking properly or releasing properly. You can see some things, but you typically don't see true function. You can see function in that my blood's flowing, but not that some of the other aspects to the blood flowing. The last modality I'll reference is just MRI, and it's a completely different animal. What they do is they put the patient into a very large magnet. That magnet causes the hydrogen nuclei or the protons of the patient to align with the magnetic field. And you say, well, where are there protons in patients? Well, your body or your hydrogen, the hydrogen nuclei, your body is made up of over half water. So there's a lot of water in you, which means there's a lot of hydrogen in you, which means there's a lot of hydrogen nuclei in you. So those nuclei, those protons, they all align with the magnetic field. Big, strong RF pulse pongs, scrambles the snot out of the protons, so they just get all jumbled up. Then in between RF pulses, as the MRI unit's listening, the protons realign back to the magnet. When they do that, they actually emit a small RF pulse. That RF pulse is detected, collected, analyzed. You get very nice structural detail out of an MRI unit, but again, primarily structure. There are some functional aspects to it, but they're different. What I'm trying to get to is each modality kind of has its own little niche. And nuclear medicine's niche is function. The last thing I want to talk about is your safety. So we've been talking a lot about radiation exposure and the cumulative damage to you, and it all kind of sounds scary sometimes. Therefore, I think it's probably best for us to talk about your safety as well as put some things into perspective. Using some of the concepts we learned today, we can control our exposure. We can use the minimal amount of source that we need. You know, if the test says use roughly this much, and I get twice that much, so I have to move my source further away, well, I'm creating more exposure for myself. Use the minimal amount of source that you need. We need to control our distance from the source, the inverse square law, right? Do I have to sit 1 foot from a source while it's calibrating, or can I sit across the room? We can limit our time with that exposure. I'm starting in a calibration that's going to take an hour. Well, lock the door, go get a drink at the cafeteria, and I don't have to be there, so I can limit my exposure time. And lastly, we can shield ourselves. You can go over to the X-ray department, grab a lead apron if you want, or those portable lead shields. Sometimes they're even in the nuclear department where you can just set the shield in between you and the source. You've just cut your exposure. But let's say you're going to be exposed. Let's compare a typical field service exposure with a cardiac stress scan for a patient. So let's start by recognizing or understanding that a 30 millicurie dose is typical for a cardiac arrest stress scan of technetium-99. So he's going to get 30 millicuries of dose. And with that, he's going to get about 15 millisieverts of exposure over the 60 hours that he's exposed for it. That 60 hours, again, is my 10 half-lives of technetium. So if I start with that as a premise, me, as a field service engineer, as a service person, I'm going to typically use between a half a millicurie and 1 millicurie of source. Well, I'm already starting out at 1/30th to 1/60th of the radiation dose that a patient's getting injected into them. Now, I'm a service engineer. I'm going to deal with it for an hour to 2 hours. I'm going to be around that source. The patient is exposed for the entire time. So now we're 1/30th to 1/60th of the time exposure. So my dose exposure is 1/30th to 1/60th. My time exposure is 1/30th to 1/60th. If we consider that I'm going to sit about 6 to 8 feet, well, I'm going to say 8 feet because of my calculations. If I sit 8 feet away from my source, and if I use my inverse square law, so doing a cardiac arrest stress, The heart is the radioactive part. We'll call it 6 inches from heart to body surface. Using the inverse square law, 6 inches is 1 R, 8 feet is going to be 16 R. Inverse square law, computed out, 1/256th of the exposure a patient's going to get. Now, if you add the 1/30th to 1/60th of the activity that was originally used, 1/30th to 1/60th the time that was originally used, and 1/256th of the actual, what all's being hit, the exposure, it's fairly safe to say we're going to receive a very negligible amount of exposure when we're doing calibrations or tests. It really is not as onerous as it sounds. I have been working with this since 1983. I have never had a radiation badge that has told me I've had an exposure that has been from anything other than X-rays, when I've worked on X-ray systems, or flights, or things like that. I have never had a single rad badge come back saying I was hot, or I had been exposed, or I've been working with source. It is a very, very, very safe modality if just common sense is used. Well, that concludes my presentation. I guess it's time to see if there's any questions.
Great, Mike. Thank you very much. Yes, we have got some questions. The first one is, why do some radiopharmaceuticals have more than 1 keV listed?
That is due to emissions. When we talk about an isotope, it breaks down or it decomposes, and there are, when it's decomposing, different energy levels can decompose, and they will create different KEVs. As atoms, or as electrons are moving from band to band, it depends on what is moving. So you can have different KEVs. Thallium has 2 peaks, we call it, around 62 or 67 to 72 keV, and then 167 keV. So there's 2 different things working. Actually, an interesting note is that technically 67 keV is in the X-ray band. So a gamma camera that's imaging thallium, the primary peak it images is actually an X-ray ray, not even a gamma ray, by true definition.
Okay, great. And so what is the difference between a nuclear scan and a PET scan?
A nuclear scan, in both cases, the patient's injected with an isotope. In the case of a nuclear scan, the emission is a gamma ray. Gamma rays, think of it as, if I take a point in space, when a gamma ray, a singular gamma ray emits, it goes in one direction, from that point in space out. Now, it can go out in any angle, but it's going out in one direction. In positron, what we're dealing with is, or in PET scan, the P in PET is for positron. And in a positron emission, actually it goes out 180 degrees from each other. So if I have an emission that is going up and to the right, there's a exact simultaneous emission going down and to the left, 180 degrees apart from each other. By using detectors that are timed very, very critically, I can see where those 2 hit on the detection ring. On a PET scanner, it's essentially a ring of detection devices all the way around the patient continuously, and whereas the gamma camera, it's just a detector. So there's many detectors in a PET scanner, and so multiple detectors will see the same event at the same time, and like that correlation and timing, that's how they determine position. Position is determined differently in a nuclear scan. It's determined by collimation. In a PET scanner, it's determined more by timing.
Okay, so is it safe for the FSE to be in the same room as a patient being scanned?
Yes, it is. Back to that last slide, we talked about the fact that you're getting 1/256th of the exposure the patient's getting, and they're only getting 15 millisieverts. So if you take 1/256th of 15 millisieverts, you're getting not very much. Plus that, the other thing to consider again is that patient, he gets injected. It was injected before he ever came into that room. He's going to be in there the whole time. And when he leaves, he's carrying the radiation with him. You're in there for half an hour, while he's in there. So you're getting the exposure time, the amount of time exposure is significantly reduced compared to what he's getting. So you add the 1/256 to, let's see here, half an hour would be 120th of the time. It just, again, things add up in a positive fashion for us as service engineers. But again, if you don't need to be there, just don't be there. In service, there are times where, as service engineers, we kind of need to be there. There's something that's happening. There's an abnormality in the function of the system or whatever that's intermittent, and they need us to see it happen. Well, we need to be there. But if you're just in there because you're bored, and you maybe want to stay away if your concern is the radiation level.
Okay, great. One other question is, do radiological materials always decay by half, or do some decay by 25% or by 75%?
No, half-life is the de facto definition of how things decay. So there is no, when half-life is a description of, I have an amount of source, and we'll give it units here. I have 1 millicurie source. In one half-life, it will be half of the original 1 millicurie. So in other words, a half a millicurie. At some point in that curve, yes, it has decayed 25% or 75% of the original, but that would not be, you'd be using some other factor other than the term half-life. You'd be trying to describe it in some other way. And the way that the industry and actually the world, as far as radiation is concerned, goes, we talk about half-life. We don't try and use any other factors. And then the time is the important thing in that. How long, what is the time to get the half-life? And that's where technetium has a 6-hour half-life. So in 6 hours, I understand, I know I can count on half of that radiation being gone. Thallium has a 3-day half-life. It's going to take 72 hours to get half of that. Each isotope has its own half-life. Even uranium or plutonium or any other radiation type that you can think of, they all have a half-life associated with them. Some of them are extremely long. Some of them are extremely quick, 15-second half-life.